This example is dedicated to the Fick's laws of diffusion. The case is simple. We have the concrete wall separating air and water regions. The initial value of water content in the wall is 10%. The concrete features some porosity, so the water diffuses through the wall. The process could be described using the equation called the law of diffusion. Here, C capital denotes the concentration, T denotes the time, and D capital is a diffusion coefficient. Our task is to simulate the transient diffusion process and calculate the water content variation in time. QuickField doesn't have interface to solve diffusion equation, but QuickField can solve the heat transfer equation. You see, both equations have similar structure. In heat transfer equation, temperature is equivalent to the concentration in diffusion equation. Okay, I will start QuickField and create the transient heat transfer problem. The problem name is Fick's law. The problem type is transient heat transfer. Remember, temperature is our equivalent of the concentration, so I will specify 10, which is 10% initial water content in the concrete. Also, I should specify the integration time. Diffusion is a slow process and takes days, so for the time step I will specify 86,400 seconds, which is 1 day. And the simulation period would be 10 days. Now here I should draw the geometry of the wall. The wall thickness is 10 centimeters and the wall height is 1 meter. Next I should switch to the Select Objects mode and assign labels to the objects. I click the object, open the Properties window and type in the name. This will be the wall. On the left side would be the air, and on the right side would be the water. Now for the water I specify 100% water concentration. In other terms, this is the temperature of 100 degrees. On the left side we have the air, so I specify 0 heat flux. The water doesn't penetrate in the air. And for the wall I specify some thermal conductivity, heat capacity, and density. I have selected these values of the ratio of thermal conductivity to the density heat capacity would be equal to the diffusion coefficient. Now let's run the simulation. I build the finite element mesh and run the analysis. And here you can see the results. Remember, the temperature 100 degrees corresponds to the water concentration of 100%. I can adjust the field picture, switch on the vectors of the diffusion gradient, and adjust the scale from 0% to the 100%. Here you can see the direction of the diffusion and the water concentration in the wall after 10 days is about 85%. We can check the dynamics here by switching the time. So initially it was only 10% of water concentration. After the first day, on the right side, contacting with the water, it's 100%, and on the left side, it is about 15 or 20% of water concentration. Then after 2 days, on the left side, is about 30%. I can also see the dynamics on the time plot. I click any point, choose the time plot, and can see how the water concentration changes in time. This way, using the heat transfer simulation, you can solve the diffusion problems. You can download simulation files from our website. Here is the link. And here our website. You can see the description of the example, and below is the download link.